Blood is an aqueous solution that supports all kinds of chemical functions in the body. If it was too acidic or too basic, it wouldn't be able to function properly. It wouldn't be able to support the chemistry that's needed for life. If there's one thing you really don't want, it's for your blood pH to be either unpredictable or too variable. In fact, it's always pretty much between pH 7.35 and 7.45, no matter how much orange juice you drink or baking soda you eat. But how is that possible? We've already seen that even a small concentration of a weak acid can bring the pH down quite a bit. One of blood's main jobs is to carry oxygen from your lungs to the tissues and carbon dioxide from the tissues back to the lungs. The oxygen hitches a ride on hemoglobin, but carbon dioxide is carried more passively. It's just dissolved in the aqueous solution of your blood. Now, carbon dioxide doesn't really stay as carbon dioxide. It combines with water to make carbonic acid, or H2CO3, with a pKa of 6.37. So if we have carbonic acid in our blood, why then is it slightly alkali and not slightly acidic? It's because blood also contains bicarbonate, carbonic acid's conjugate base. And because of the common ion effect, the pH of the overall solution depends on the balance between the two ions. So if we make a few assumptions, like that exhaled air contains around 4% carbon dioxide, and the pressure of your breath is probably above atmospheric pressure, so let's call it around 1,000 millimeters of mercury, and Wikipedia tells me that the dissolution of carbon dioxide in water is around 0.03 millimoles per millimeter of mercury. So that would be 1.2 times 10 to the negative 3 molar concentration of carbonic acid. And according to the Henderson-Hasselbalch equation, to get a pH of 7.40, we just need to find the pKa of carbonic acid plus the logarithm of the bicarbonate divided by the concentration of the carbonic acid, or 1.2 times 10 to the negative 3. And so for that relation to hold, we find that the bicarbonate concentration has to be 1.286 times 10 to the negative 2 molar. Now that combination of carbonic acid and bicarbonate is called the bicarbonate buffer system. And it's important for our blood's homeostasis. It maintains the pH of our blood. But I still haven't explained what a buffer is or how it works to stay at pH 7.4. A pH buffer solution is one that resists change in pH, typically by containing a mixture of a weak acid and its conjugate base. Let's see why with blood in our example. Let's say that for whatever reason there's an amount of strong acid introduced into your blood so that it creates a concentration of hydronium at 1.0 times 10 to the negative 5. If your blood was just pure water, that would drop the pH 7 to pH 5. 2 whole pH units away and way outside of the range you need to stay alive. Because of your blood's bicarbonate buffer system, the hydronium first affects equilibrium by shifting the concentration balance of the two ions. Let's use an ice table to see exactly how this works. The hydronium is going to subtract that amount from the bicarbonate and add that same amount to the carbonic acid. And we can plug our new values into Henderson-Hasselbalch to find 6.37 plus the logarithm of the new concentration of base to acid equals pH 7.396. So the buffer solution meant that our blood pH would only change by 4/1000ths of a pH unit, still well inside the normal range, and far from the 2 full pH units that just pure water would have changed. Of course, there are limits. If we add more acid than there is bicarbonate, then we exceed the buffer capacity and the pH is going to drop sharply. We could increase the buffer capacity by adding more of the conjugate pair ions, but that also increases the overall concentration of dissolved salts in the solution, and that may not be possible for some applications. High salt concentrations can be quite toxic to living systems, for example. Using a method called titration, we can also use that sharp change in pH to measure the initial acid or base concentration in unknown solutions. We'll hear more about that next week.